Okay, so the next part of the MCQs, we're going to start with question 16, and it was asking for the units of the ratio of specific heat capacity versus latent heat vaporization. So again, you can go back and you could work this all out from the equations, but you can always remember specific heat capacity was joules per kilogram per Kelvin, whereas latent heat of vaporization didn't depend upon the temperature, so that was just joules per kilogram. So in this case, my joules per kilogram both cancel out, just leaving me with per Kelvin, so K to the minus 1 in this case. Again, you can just remember specific heat capacity. Okay, in case of this way, it's like Q divided by MT, and for latent heat vaporization, it's Q over M, if you wanted to go back and do it from the original equations. Question 17 was asking us about the increase in the change in pressure if we opened up this valve. So we've got Q and we've got R. So we have P1 V1 and P2 V2 for each of these. And in this case, we're going to open the valve up, so we're going to have a new system of P3 V3. So in this case, I've got 3V and 1P for Q. For R, I've got 3P, like 3 times the pressure. It's told me that up in the question, and I've just got 1 volume. Again, with this case, because we open it up, we've still got a total volume of 4V. I've just added my 3 volumes to my 1 volume together, but I don't know what the P is, so I need to find out what P is first of all. So in this case, okay, we have got, let me just solve those together. We've got 6 VP, and in this case, we've got to get this to equal 6, so 4 times something equals 6, well, that is actually 1.5. So that means that my pressure, okay, in this case, we're going to compare it because we're looking at the change in Q. So originally, we started at 1 pressure and we've now gone up to 1.5 pressure. So Q has gone up, okay, by an increase of a half in this case. So we've gone from 1 pressure to 1.5 pressure. Okay, so the new one, the original one is 1, the new one is 1.5, it's increased by 0.5, so it's plus, but the pressure over 2, because it's only half the pressure going up there. Okay, for 18, it was asking about simple harmonic motion, and acceleration of the object is never constant. We know acceleration changes throughout. It is not directed away from the centre, it's directed always towards the centre. Okay, it's always directed that the force is acting in. It is not a maximum at the centre of the oscillation. Remember, it is 0 at that point. Okay, it is maximum at the extremes of the oscillation. So I was just going through process of elimination here, or it's actually, just if you learn the acceleration relationship with some harmonic motion, you also just know it's D straight away. Next one then was also talking about displacement of a particle in a travelling wave, and it was asking me to do a little bit of determining things from the graph. So the first thing is it was asking me the frequency and the amplitude. Well, the first one, I can really easily work out the amplitude here, okay, in micrometers. Okay, it's already in 10 to the minus 6. In this case, it's an amplitude, so it starts from 0 and it goes up to 2, so it had to be A or C. At this point, I want to work out the frequency. Well, I've been given the time period. Okay, so the time it takes for one wave to travel, so that's this distance here. Okay, from here to here, this is my time period, which is 20, and frequency is 1 over the time period. So I shouldn't say it's 20, it's 20 times 10 to the minus 6. So 1 over 20 times 10 to the minus 6, well, if we know 1 over 2, it's going to give us in factors of 5. The other one was 20 anyway, so I already know by process that it's going to be 50. It can't be the 20, because it's 1 over 20, so it's going to be this one here, 50 and 2. 20, again, should have been a quick one. You just look at it and solve. This is where you make your marks up in an MCQ. Not all of them are going to take you a minute and a half. Some of them are going to take you longer than a minute and a half to solve. Simply look at this. We know that which waves cannot be polarised. No longitudinal wave can be polarised. Only transverse waves can be polarised, which meant ultrasound, that's the only longitudinal wave. From my fundamental frequency, it's fixed at both ends, so I just drew out my first harmonic. Okay, and in this case, my fundamental frequency, my first harmonic, is giving me the length of the string would be equal to half a wave. Okay, now V is equal to F lambda. We know that lambda then is V over F, so I've got 480 over 400. Now, you need to make sure you can do this in your head, like 48 over 40, or 48 over 4 is, 12, but then that's obviously 40, so you'd move it down to 1.2. Just make sure you can do some quick, simple mathematics. I had a little look at some people's work, and I was thinking that might be something that a few people maybe need to have a little bit quick look at. In this case, that is the wavelength. That is not the length of the string, because the length of the string is equal to half of the wavelength. So it's half of 1.2, so it's 0.6. So coming out to be the answer of B. We then have the next one. Two satellites, W and X, have the same mass. Okay, they have circular orbits around the same planet. Okay, well, again, you could go through process of elimination, but also I'm going to just kind of give us the explanation of why the answer is D. Okay, each of these actually will increase, but with the other one, we want it to be smaller. Well, the time period, okay, the orbital period in this case, is directly proportional to the r cubed. So if we decrease the radius, we decrease the time period, going back to our Kepler's third law there. 23 was a challenging question. I'm going to do a separate video on this, just to kind of give you the working here about breaking slopes and how they're affected by them, because I'll go through the mathematics in a different video. But essentially with this, okay, we know that as the force, the centripetal force, is acting towards the centre of the circle. Well, in this case, we will need to have some more friction, okay, to increase the speed in here to make this a larger force, okay, because F is equal to mv squared over r. So if we want more v, we want more centripetal force. So I want to have an increase of friction. Also, to help me increase that centripetal force, okay, again, I also need to have a steeper angle. But again, I'll do that in a separate video for you guys, just because it's going to take a little bit long to go through. 24 was a nice old dealing with our vertical components of a circular motion problem, but it was asking us in a slightly different way what the kinetic energy was rather than what the size of the force was. So in this case, I wrote, well, kinetic energy equals a half mv squared. Centripetal force is mv squared over r. Well, so therefore kinetic energy in this case is going to equal, well, half r times f, because if I did mv squared, that's rf. So I can also sub those in there. Now, we know mv squared over r in this case is mg plus t, because at the top of the circle, the string is pulling it down, so we've got the tension, and we've got mg, so it's going to be equal to both. So in this case, my rf, in this case, is also equal to mg plus t. So simply plug those in, so rf is equal to r times mg times t, and I've got over my 2, which essentially is this here. So, apologies, that was my cat, who should go away now. The next one then was another good old little ratio problem. They do like ratio problems on the IB, and it's something that we don't find as easy. It's something that I would suggest getting a bit more practice with. So in this case, we were being asked about the radius of the Earth. So every time I do a ratio problem, I like to do a little grid and write down what I have at the beginning. So I'm looking at Mars compared to Earth. So we know Mars has a quarter of Earth, so I said it's g over 4. Earth's is just g. Mars has a mass of m, so Earth's mass is 10m, radius of Mars and radius of Earth. So I go back to my equations, looking at g is equal to gm over r squared. Well, in this case, I can then simply rearrange for r squared, so r squared of Earth over radius of the Earth squared over radius of Mars squared. In this case, it's going to be like 10 gm over g over 4. Okay, essentially here I can start cancelling lots of things out. I can cancel my gm's, I can cancel my g. Okay, that 4 comes up, it becomes 10 over 4. Well, that's squared, so remember I want to then take the root of these, so I've got root 10 over root 4, which is root 10 over 2. Well, at this point I was like, well, I don't know what root 10 is off the top of my head, but I know root 9 is like 3 over 2, so that would be like 1.5. It's giving me the right sort of scale factor there, so it's going to be in the 1.6. Okay, if you know root 10, great. I didn't, so I kind of just used something to help me out with one that I did know, to give me a bit of a sort of help there. Number 26 was one of these diffraction grating resolution questions, which is something that you guys had been wanting to do a little bit more revision on, so I'm hoping that this one went okay for most of you. So in this case, we're using lambda over delta lambda is equal to mn. well, we had 590 nanometers over 0.59 nanometers. The nanometers cancel out, so I didn't bother taking them into consideration at this point. And it's asking me at the fourth order grating, so I had to put my m in as 4 to work out n, so it's just 1,000 over 4. In this case, 590 over 0.59, I should say, gave us 1,000. Divided by 4 gives me 250. Ooh. My next one as well was a little bit more maybe of a question that you had to think about a little bit, but again, it's just simply using our simple equations and rearranging them in a way that we can make sense of. So we have light of a frequency of 500 terahertz is incident on a single slit in the forms of diffraction pattern. First diffraction medium forms an angle of this, so to the centre maximum. The frequency is now changed to 750 terahertz. What is the angle? So at this point I'm thinking, okay, well, what am I going to have to do? So to try and work out this new angle, because I can't calculate that from the top of my head. So theta is equal to lambda over b. We're dealing with a single slit. Okay, so single slit is obviously using this equation here. I've been given frequency rather than wavelength, but I know v is equal to f lambda, so I can also say that theta is equal to v over fb. Now, my speed of waves isn't changing, it's just speed of light, and my b is also not changing, so that is a constant. Okay, so I know that theta f, okay, if I move my f up here, is equal to v over b. So I've used that to say, okay, I know that theta f is equal to v over b, some constant. So my theta f of this must equal my theta f of this new one. So I had 500 times 2.4 times 10 to the minus 3 is equal to 750 times, well, what? Well, in this case, I'm not going to be able to calculate this, but I can use, again, some sort of little simple ratios. I know that 500 has jumped up to 750. It's gone up by a factor of 1.5, which means that my angle must also go down by a factor of 1.5. So 2.4 going down by a factor of 1.5, okay, is simply 1.6. All right. So again, with that, I could just use my little ratios to kind of help me with that question. The second one then as well was also looking at a single slit, but it was using that little relationship there that you're not given in the data booklet, but you are expected to know. And we're using an eye. So in this case, I've also got a circular aperture. So we have cars with a lambda of 400 nanometers, car with a wavelength of 400 nanometers, and they're separated by 1.2 meters. We're looking at the point of resolution. What distance can we see those? So we have 1.22 times lambda over b is equal to s divided by d. In this case, I simply just put my values in. So 1.22 times 400 times 10 to the minus 9. I do need to look at them this time because I have got them in different units here. 4 times 10 to the minus 3 is equal to 1.2 over d. Simply then rearrange for d, so that was 1.2 times 4 times 10 to the 3 over 1.22, 400 times 10 to the minus 9. Well, 1.22, again, because I'm not using a calculator, I'm just going to say they're pretty much equal and cancel them out. So that left me with 4 times 10 to the minus 3 over 400 times 10 to the minus 9. Again, you can bring this all back into this sort of standard, using your standard form, like 10 to the minus 3, take away like 10 to the minus 9. Essentially, it leaves you with 10 times 10 to the 3 when you put those in there. Okay, so it leaves me with 10 kilometres. Again, you could have just seen 4 divided by 400 is going to give you a factor of 1, so it has to be the b as well. Okay. 29 then was looking at our simple harmonic motions. So with this time we were given a displacement time graph, and we were being asked to find the velocity. Okay, remember we always said that going from our our x graphs to our velocity graphs to our acceleration graphs, we always were taking the derivative to go down to them into the next one. Okay, so we derived v is the derivative of x, a is the second derivative of x, it's the derivative of v going through. So I looked at this and I said, okay, all of these have basically got the same sort of function here. It's just depending whether it's a minus sine, a sine, a minus cosine, or a cosine. So I just went with, well, this graph is a negative cosine. Okay, v is the derivative, so it must be a positive sine graph. Okay, you could also use your phase difference ones to work this out as well if you wanted. But essentially here, I just said, okay, this is going to be, this is the derivative of it, so it's sine. And then the last one Okay, actually you didn't have to work anything out because they gave you the calculations here, but you just needed to it was kind of testing on could you recognise when to use the correct Doppler effect equation. So in this case you had to always work out what's moving and what's stationary. In this case we had a moving source, so I had to use my moving source equation, and then I had to work out if it's moving away or towards. It's moving towards the person, so I had to do V minus U in this case. Remember, you in the equations you're given plus or minus. When it moves towards, you use the minus part of it. Just plug the values in at this point. 330 take away 40 to give me 290 over there. And